Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving into Sir Michael Atiyah's insightful 2002 lecture, Mathematics in the 20th Century. A fascinating overview, wouldn't you say?
Absolutely. It's amazing how much ground he covers. I'm particularly interested in his discussion of the shift from local to global perspectives. He uses complex analysis as a prime example, right?
Precisely. He contrasts the 19th century focus on explicit formulas for functions with the 20th century emphasis on global properties like singularities and domains. It's a beautiful illustration of a broader trend in mathematics.
And that's not limited to complex analysis. He extends this local to global theme to differential equations and even number theory, comparing local and global theories in a really elegant way. It's almost poetic, the way he connects these seemingly disparate fields.
I see. Yes, the analogy is striking. He also highlights the increase in dimensions, moving from one complex variable to multiple variables, and from curves and surfaces to higher dimensional manifolds. This shift wasn't just a quantitative increase. It fundamentally changed the nature of the problems.
Exactly. It forced mathematicians to grapple with concepts that were harder to visualize, pushing the boundaries of intuition. And then there's the fascinating transition from commutative to non-commutative algebra, spurred by Hamilton's quaternions and the impact of quantum mechanics.
Yes, that's a crucial point. The non-commutative nature of quantum mechanics profoundly impacted algebra, leading to new areas of study and applications. He also discusses the move from linear to nonlinear systems, highlighting solitons and chaos as key examples of nonlinear behavior.
Right, and the contrast between solitons, this unexpectedly organized behavior, and chaos is particularly striking. It shows the richness and complexity of nonlinear systems.
He then delves into the age-old tension between geometry and algebra, framing it as a philosophical debate. He cleverly uses the Faustian bargain as an analogy, suggesting that algebra, while powerful, can sometimes lead to a loss of geometric intuition.
That's a really insightful analogy. It highlights the potential dangers of over-reliance on purely algebraic manipulation at the expense of geometric understanding. But he also acknowledges the value of both approaches, emphasizing that they are complementary rather than mutually exclusive.
Absolutely. He then shifts to discuss unifying techniques like homology theory and K-theory, showing how these tools transcend disciplinary boundaries. It's remarkable how he connects these to seemingly unrelated areas like topology, algebra, and even number theory.
The breadth of application is truly impressive. And the discussion of Lie groups and their role in unifying different geometries is equally compelling. It's a testament to the power of abstract mathematical structures.
Yes, he also touches upon the classification of finite simple groups, acknowledging the controversy surrounding its importance. However, he highlights the monster group as a particularly exciting discovery, opening up new avenues of research.
That's a great point. The monster group is a fascinating example of how even seemingly complete classifications can lead to unexpected and significant discoveries. And his discussion of the impact of physics on mathematics is equally compelling.
Indeed. He traces the influence of physics from classical mechanics to quantum field theory and string theory, showing how physics has both driven and enriched mathematical development. The interplay between these fields is truly remarkable.
He concludes by speculating on the future of mathematics, suggesting that the 21st century might be the era of quantum mathematics, or infinite-dimensional mathematics. It's a bold prediction, but given the trends he's outlined, it seems plausible.
It's a thought-provoking conclusion. He mentions Kone's non-commutative differential geometry and Arakelov geometry as potential areas of significant development, and he also emphasizes the continued importance of low-dimensional geometry, highlighting its mysteries and connections to physics.
A truly comprehensive and inspiring overview. It leaves you with a sense of wonder and excitement about the future of mathematics. Thank you for this insightful discussion.
My pleasure. And thank you to our listeners for joining us on Tech Bytes and News. We hope you enjoyed this deep dive into the fascinating world of 20th century mathematics. Have a great day.
Bye-bye.